Okay, let's talk about one-to-one functions. So what does it mean to be a one-to-one function, numerically, graphically, and of course, we're going to analyze it algebraically. So start off with our basic definition of a function. So here's your basic definition. There is a relationship where every x value gives you exactly one y value. Okay, so that's what a function does. You give it an x, it gives you out some other, right, an output. So if we had this point, 2, negative 3 on some graph, that would mean that no other point can have an x value of 2. Because the only x value goes to positive, or rather negative 3. Okay, so that's what it means to be a function, is that every x gives you exactly one y. But a one-to-one function means this. It's a function where every y value comes from exactly one x value, right? Because it's possible to have, like it says here, 2 of the same y value from different x values. Right? If you think about a quadratic, right? If you think about y equals x squared, if we square negative 3, right, that's 9. So if we have an x value of negative 3, we have a y value of 9. Similarly, if we have an x value of positive 3, we also have a y value of 9. And a quadratic is, in fact, a function. But it's not a one-to-one function. Okay? In a one-to-one function, you only get one y value for every x value. Rather, for every y value you get, it came from exactly only one x value. And you can't get 2 y values. No, you can't get the same y value from 2 different x's if your function is one-to-one. Okay, so let's talk about some generalities and how we determine if a function is one-to-one numerically. Right, so here we're going to be looking at tables of values or a point relation. And then we're going to look at it graphically. What does that mean if we have a graphical? And then we're going to look at it analytically. Okay, we're going to analyze an equation. Okay, so let's see what those mean. So here are all of your determinations. Okay, so pause the video and write them all down. Discrete, we can have no repeated y values, or your y values have to decrease from right to left. Okay, for a graph, we're looking at the horizontal line test. Okay, if it crosses your graph more than once, then your graph is not the graph of a function. Okay, it can only cross it once. Your graph is not one-to-one. It can still be a function, it just wouldn't be a one-to-one function, because here you have multiple y values from different x values. And then analytically, like an equation, it really depends on the equation, unfortunately. But quadratics will never be one-to-one, and absolute values will also never be one-to-one, unless they have some type of a domain restriction, which they usually don't. So let's talk about the inverse. Okay, the inverse of a function is one where you switch your x and your y values. Okay, so we're always switching your x and y values when we're doing inverses. The domain is your x stuff and the range is your y stuff. So what property must exist? Well, your graph must be one-to-one. In order for the inverse to be a function, your equation must be one-to-one. For inverse to be a function. Right, so we can have an inverse, it just wouldn't be a quote-unquote function. Okay, a function is one where every x value gives you exactly one y value. Okay, and so something is not a function, right? Think about a horizontal parabola. Right, this x value gives you a y value here and another y value there. Okay, so this horizontal parabola is not the graph of a function because it fails your vertical line test, right? There are 2 y values for a given x value. Okay, and that's not the definition of a function. A function has every x giving you exactly one y. So now let's talk about the things about inverses. Okay, 3 different types of inverse determinations. So when we have a table and you want to find the inverse of those values, you just switch in the x and the y. Okay, simple enough. If you have a graph, okay, the graph's inverse is a reflection across the line y equals x. Okay, so you take every point on your graph and you switch them, right, y comma x, and then you replot that point. And then if we have an equation, right, this is where the algebra comes in. You switch your x and your y variables. You solve that equation for y again, and then the last thing you do is you replace y with y inverse, so we have the correct notation, right? You don't want to have y equals because that's what you started with. We want to have y inverse, or the equation for the inverse of y. Okay, so don't forget about that last step, replacing y with y inverse. So let's take a look-see in what we got. It says determine if the inverse exists, providing justification. Okay, and it's the justification part that we do here in pre-calculus that is unlike other things that you have done before. Okay, if it does exist, actually find the inverse. Okay, so give a table. If it's a graph, do a graph, and if it's an equation, find an equation. Okay, so that's our directions for what's going on here. So let's see what we have. Looking at A, right? A is a relation, so it's a bunch of points. What do you notice about the y values from this table that now we can't see on the video anymore? Hopefully you're noticing that this has a y value of 2, and this one over here also has a y value of 2. So the question is, does an inverse exist? We would say no. F inverse does not exist. And why does F inverse does not exist? Because f of x has a repeated y value. Right? That was our determination from a couple of minutes ago, that if we had repeated y values, then our function was not one-to-one. Okay? And an inverse does not exist if f is not one-to-one. Okay? So by the fact that we had some repeated y values, that makes our function, or in this case our discrete relation, not one-to-one. And if our function is not one-to-one, then the inverse does not exist. Okay, here's B, so I have to rewrite these. This is a 6 and a -2, a -1, a +2, and a 3. So, does an inverse exist? Right? Yes, it does, because f of x has no repeated y values. All of your y values are unique. Therefore, f of x is one-to-one. Okay, so because it's one-to-one, we can write the inverse relation. So we're going to make our own table, and we're going to put the points in there as an inverse. So here's our inverse relation, right? So it's f inverse. The inverse does exist because our function is one-to-one, because we have no repeated y values in your table. Okay, so let's look at this graph here, our nice, not very clear graph. But does an inverse exist? Okay, and we would say yes, f inverse exists, because if it's a graph, we have to apply the horizontal line test. So if we draw a horizontal line anywhere on our graph, how many times does it cross? Only once, because the graph of f of x passes the horizontal line test. And we're going to use HLT to abbreviate horizontal line test. Okay? So the inverse does exist. The reason why it exists is it passes the horizontal line test. So f of x is one-to-one. And all one-to-one functions have inverses that are also functions. So we're going to plot this. So let's write down all these 4 points from our graph. So there, the purple is the graph of our inverse from our original f graph. Okay? And then lastly, number 4 here, is this a one-to-one function? Right? And no. So once again, we can draw the horizontal line test, and this crosses our graph here 3 times. So we can say that G inverse, since this is called G inverse does not exist. Because G, right, is not one-to-one. It fails the horizontal line test. Okay? So it has no inverse function, right? The inverse is not a function because your graph is not a one-to-one graph because it fails the horizontal line test. Okay? So there is our description, right? Things being one-to-one. If it is one-to-one, then the inverse does exist, and it is a function. And if it's not one-to-one, then the inverse is not a function, and therefore does not exist. So let's try some algebra problems with this now. Here we have another graph of this nice curvy-looking function. Okay, sorry, my video is very blurry. It's my program's about to crash, so it'll clear up here soon. But until it does, we're stuck with this. So it's a graph. Does it pass the horizontal line test? Yes, it does. So we can clearly say that yes, the function inverse, the inverse does exist. Okay, because our graph is a one-to-one graph because it passes the horizontal line test. So there's the graph of our inverse. Okay, it passes the horizontal line test, which means the graph is one-to-one, and the inverse exists. Okay, now that we have some functions, I believe, so let's rewrite these functions so you can see exactly what they say here. So what can we say about this quadratic? Okay, we can say that this is not a one-to-one function. Okay, because it's a quadratic, none of the quadratics are one-to-one functions. So f inverse does not exist. Okay, it's not actually going to be a function. Does not exist. Okay? No quadratics that don't have a domain restriction. If we had a domain restriction on there and it wasn't an actual u, then you would have a no inverse function, right? Does not have one. Okay, so let's see, what else do we have here? This one's really hard to read, so let me rewrite it too. So 2/5 x minus 3. What type of a function is this? This is a linear. So f of x is one-to-one, right? Because it is a linear function. In fact, this is an increasing linear function. Okay? It's always increasing from left to right. And I know that it is an increasing linear function because I have a positive slope. Right? A positive slope means we go up 2 units and right 5 units to get a new point. So up 2, right 5, right, is an increasing slope. So we have an increasing linear function. That means f of x the inverse does in fact exist. So now that we know the inverse does exist, let's find it, the equation for it, rather. Let's find the equation for our inverse. Okay, so our steps are first, replace x with y. Replace x and y. So everywhere we see an x, you're going to put a y, and everywhere you see a y, we're going to put an x. So x equals 2/5 of y minus 3. Now let's do our simple math. So the simple math here says add 3 to both sides. Okay, x plus 3 equals 2/5 times y. Okay, so now we have a couple of options on how to deal with this. One option is to get rid of your denominator, and we get rid of our denominator by multiplying. So we're going to multiply both sides by 5. Okay, so 5x plus 15 equals 2y. Right, so maybe now the last step would be divide by 2. Okay, and there's lots of ways that we can interpret this, right? You can write, you can leave it just like that if you want to. You could bring the 2 to the front and make it 1/2 of 5x plus 15. Okay? You could divide each of these separately and make it 5/2 x plus 15/2. Right? That's another way to do it. You could also write it as a decimal, 2.5x plus 7.5. Right? All of these are correct, including, in fact, all of these, all the way up here to the top, all of these are correct. Any one of those ways that you want to write it. Okay, they're all correct. But they all equal y inverse, okay, because this is the inverse of your given linear equation. Okay, these ones are inverses of each other. Okay, so lots of ways that we can write a linear equation, especially when it has a fractional slope. Okay, and this is our last algebraic one here that you can't see, so let me write it down too. So this is a square root function. So we know that the inverse will exist because this is a one-to-one function. Okay, all square root functions are one-to-one. Okay, so we start by switching your x and your y. So x equals 2 times the square root of y plus 3 plus 4. Okay, so we'll do the easy algebra first, which is minusing 4 from both sides. So x minus 4 equals 2 root y plus 3. And then the second easiest is dividing by 2. Okay, so I'm going to write this as 1/2 x minus 2. Okay, just to keep it kind of simple. So I took half of x, right? That's divided by 2, it means half. And 4 divided by 2 is 2. So now that I have my square root all alone, I can square it. So I put this in parentheses and I square both sides. Okay, on the right side, this cancels out. On the left side, I'm not doing anything. I'm just going to leave it as parentheses squared. I don't want to have to multiply that out unless absolutely necessary. And right now, it's not absolutely necessary. If you make it to calculus, it also won't be absolutely necessary to multiply that out. Okay, so that would be my answer if I could have both sides of my quadratic. So let me explain this to you. Right, this has a domain restriction of x has to be greater than or equal to -3. Okay, and I get that by setting my absolute value greater than 0, right? Because I can't take the absolute value of a negative, which means anything smaller than -3 I can't use. So I have to incorporate that domain restriction down here. Okay? Because it's not both sides of my quadratic, it's only going to be the right side of my quadratic. And there's the bell. So we are done for the day. Okay, so if your function is one-to-one, then the inverse exists. And if it's not one-to-one, then the inverse is not a function for lots of different reasons.